Welcome student for the second lecture, structural analysis, and we are discussing the topic slope deflection equation. Now today we will see how the slope deflection equation is developed. So as we know that the final end moment which is equal to the fixed end moment due to the external loading, moments due to the end rotation and moment due to the deflection at the end, which is nothing but the final end moment. Now, application of slope deflection equation is nothing but to calculate the final end moment. Okay, and that final end moment we will see here. Before start the equation, we will see the sign convention. For anticlockwise movement, it is positive, and the clockwise movement it is negative. Similarly, for a deflection also, the downward deflection we will consider as a negative and the upward deflection we will consider as a positive. Now the sign convention for the moment in slope deflection method. For a simply supported beam, the resisting moment is negative and end moment is positive. If the bending action is hogging, the upper diagram of this beam, and in the lower beam, that is the beam AB, we can say that the sagging moment, that is resisting moment positive and the end moment is negative, and the opposite moments at B, that is the end moment is positive and the resisting moment is negative. Okay, if the bending action is sagging, right? Now, sign convention for the movement in slope deflection method if your beam is fixed. So, due to fixity, the slope at the end is zero and the movements are clockwise. Suppose it is a clockwise, which is positive, and the anti-clockwise is negative. Now, the due to the settlement of the support, the you know B joint is settled in downward direction. So let that delta is nothing but the settlement, okay, at joint B. So due to the settlement of support B, the whole beam is rotated in a clockwise direction, okay, and we consider as the moment, we consider as a displacement or a settlement is positive. Now at A, the displacement is same, okay, but which is negative, okay. At A, delta is negative, and at B, the delta is positive, right? Now, uh, we will consider a continuous beam which is fixed at end A and simply supported at C. Now, L1, L2 are the span for a beam AB and BC. Uh, Now, first of all, we consider as the joint B is a fixed support, or we consider the span AB. AB is fixed and BC is also the fixed. So, in the step number one, we calculate the fixed end moment. Okay. So, as per the definition, we know that the final moments is equal to the fixed end summation of all the moments, and the first moment is fixed moment. Okay. So WL square by 12, which is nothing but the fixed end moment for a UDL loading. So AB is supported to the UDL and WL1 square by 12. So positive, it is a anti-clockwise direction is positive, and the clockwise direction, that is WL1 square by 12, which is nothing but the negative. So similarly, entire beam is loaded as a UDL. So the formulae for the fixed end moments are the same for all the joints, that is WL square upon 12. For A, it is positive for AB, and for BA, it is negative. Now, this is the bending behavior we can see in this diagram. So for AB, it is a sagging moment, and for span BC, it is a you know uh, the behavior like upward and the downward, sagging and hogging, both the bending action we can see. So due to fixity, theta A is 0 at this point. At that point, the theta A is 0 and the bending is, sagging moment is generated like this. Now at point B and at point C, what happens due to the UDL, it is go in a, upward direction, then after it is comes in a downward direction. Okay. So this is the bending action of the beam due to the UDL loading, right? Now, the end moment due to the due to the rotation span for the AB. Now, the rotation due to the theta A, but due to fixity at end A, theta A is 0. If you see the support, it is a fixed support, and that's why the slope at this point is 0. Okay, and the movement generated due to the, that rotation is 4 ei theta a upon L1, which is nothing but the positive, right? Because it is in an anti-clockwise direction and as per our sign convention, it is positive. For BA, it is a clockwise direction and as per our sign convention, it is negative. Okay, so this is nothing but the half of this, half movement of the A, which is nothing but 2 ei theta upon L1. Now, if you see the span AB, the rotation due to theta B. Now, in the first case, we see the rotation due to theta A. It means that we are releasing the joint A, and in the second point, we are releasing the joint B. So, for the rotation due to theta B, so for B joint, it is 4 ei theta B upon L1, and the for A joint, which is nothing but the half of the D, that is 2 ei theta B upon L1. Okay. So, this is the part of analysis. It means we are analyzing the beam as each end. Okay, first of all, we are releasing A, okay, and we fixed at B. Then after we are releasing B and we fixed at A, and the close end or the end which we are going to be released, the moment at that joint is 4 ei theta A upon L1. Okay, so in the first case, we are releasing at A. Therefore, the at joint A it is 4 ei theta A upon L1, and at point B it is a half of A, that is 2 ei theta A upon L1. In the second case, we are releasing the joint B, so the rotation due to theta B. So that's why 4 ei theta B upon L1, and half of this B, which is produces at joint A, that is 2 ei theta B upon L1. Now this concept is very important to develop the slope deflection equation. Okay. Now, the end moment due to the rotation for the span BC. Now, for span BC, the bending behavior already we seen that for B to C, the entire UDL is there, and the bending action, which is, hogging upward movements, that is theta B, and and which is again sagging for a downward bending behavior up from B to C. Okay. Now, here also we see the rotation, first of all, rotation due to the theta B and then after rotation due to the theta C. Now, for rotation due to theta B, at point B, the 4 ei theta B upon L2, and at B, which is half of the at C, which is half of the B, which is 2 ei theta B upon L2. Now, similarly, the rotation due to theta C, it means that we are releasing the, joint C and the joint B is fixed. Okay. And therefore, the rotation due to theta C, which is nothing but 4 ei theta C upon L2, and at B, which is half of theta C, that is 2 ei theta C upon L2. Okay. Now, when we consider the rotation due to the movements, now second and the third part is that the uh, end movements due to the deflection, or we can say the settlement. Okay. Now this is the continuous beam ABC, and the delta that is the settlement at joint B. So due to that, the moments at A is 6 delta upon L square, and at B also 6 delta upon L square, and C also 6 delta upon L square, because the vertical displacement, or we can say the settlement, the any supports is going to be settled down in the downward direction or in the upward direction. The same displacement, the same deflection occurs at each and every joint. Okay. Now only the question is that the sign convention, right? Where it is positive and where it is negative. So as per our sign convention, if you see the joint B is settled down in the downward direction, if you see the C support and A support. So A supports is your, left side, and C support is in your right side. So left side is negative and right side support is positive. So you keep it in mind always. The supports, where the support is going to be same, the left hand support and the right hand support. So right hand support is positive and the left hand support is negative. It means the moments at A is, negative, and the moments at C is positive. All right. Now, final movements, that is MAB, we can calculate by taking summation of all these movements. So MAB is nothing but MAB fixed plus 4 EI theta A upon L1 plus 2 EI theta B upon L1 plus 6 EI delta upon L1 square. Now, how this equation comes? Now, let us see. First of all, the MAB, which is nothing but the final moments, okay, which is equal to MAB fixed, okay, plus 4 EI theta A upon L square. So the first diagram you can see here. So these are the MAB WL1 square upon 12. These are the MAB fixed end moments. So MAB fixed. So we can write down M bar AB also. So M bar AB is nothing but the fixed end moment, plus 4 EI theta A upon L1 and 2 EI theta B upon L2. These two equations, that is, first of all we are releasing theta A, then we are going to be releasing theta B for the joint A. Okay. Now this is the equation MAB. So M bar AB, that is the fixed end moment, plus 4 EI theta A upon L1 plus 2 EI theta B upon L1 plus 6 EI delta upon L1 square. Now this term 6 EI delta is nothing but the settlement of the B joint, and the moment produces due to that settlements. Now, if you take a common 2 EI upon L1, so MAB, this is the fixed moment, okay, M bar AB, and 2 EI L1 is we taken as a common. So, in bracket 2 theta A plus theta B plus 3 delta upon L1, okay. Now, here we are taken a positive sign, okay, because in problems we don't know where the which supports is going to be settled. Okay, so as per the that location of that displacement, it may be a upward direction, it may be a downward direction, or sometimes the right hand supports may be synced or the left hand supports may be synced. So as per that, the sign may be changed. If your right hand support is synced, it is positive. If your left hand support is, we are taking the moment, so it is negative. So that's why that plus sign is there. Okay. So similarly, for a BA, that is the movements from B to A, so MBA is fixed range support, 2 EI theta A upon L1. You can see the, diagram here, rotation due to theta B, that is 2 EI theta B upon L square plus 4 EI theta C upon L square and 6 EI delta upon L square. So for span BA, you can see here MBA fixed 2 EI theta A upon L plus 4 EI theta B upon L1 plus 6 EI delta upon L1 square. Now if you take common for 2 EI upon L1, so final end moments for the span BA which is equal to MBA fixed plus 2EIL1 in bracket theta A, okay, plus 2 theta B plus 3 delta upon L1. Again, the sign of delta which is depends on the location or a joint of support, okay. So this equation is known as the slope deflection equation, okay. Now in this chapter, the slope deflection equation, we see the various problems for frames and the beams, how to calculate the final end moments by using the slope deflection equation. Also the bending moments and the shear force diagram also we will see. Okay. So theoretical part is completed for this unit, and for from the next lecture we will start the numericals. Right. Thank you for the watching.